Hello everybody, this is the second part of 4.3. For this part we are going to talk about the higher derivative. Okay, so don't forget that previously we have learned how to find a partial derivative either with respect to x, okay, which is using this kind of notation, or a partial derivative with respect to y, and we use this kind of notation, the df by dy or f sub y. Okay, so if we find further derivative, okay, either from f sub x or f sub y, okay, we can do, for example, the first one you find the derivative with respect to x, and then another one by x, okay. This one is called the second derivative, okay, which is f sub xx, or sometimes we use the notation look like a fraction, so it is a d2f by dx square. Okay, d2f by dx square. Of course, I mean, if you start from f sub y and then you find further derivative with respect to y, this is another second derivative of your function f. We call it f sub y. Okay, or in terms of this fraction notation, it is d2f by dy square. Okay, d2f by dy square. Okay. However, if first we find a derivative with respect to x and then continue to find a derivative with respect to y, this one we call f sub xy. And if you use a fraction notation, this one you need to be very careful, because for the fraction notation, the operator, the derivative or the differential operator, it will put it in front of the previous one. For example, this one, it means that you find a derivative with respect to x first and then continue by y. Okay, so this was d2f by dy dx. Okay, d2f by dy dx, but the order of derivative start from this one to the front. Okay, not like this. If you use the notation as a subscript, okay, the first one will be the one that close to f, and then the order of derivative will go from left to right. Okay, so if you find the derivative with respect to y first, followed by the x, then for the subscript notation, you are going to write f sub yx, okay, from left to right like this. But if you use the fraction notation, you are going to write your d2f by dx dy, and the order from your right to left. Okay, so this one is somewhat a little bit different between two notation, and sometimes it will make you confused, so you need to look at it carefully. Okay, the subscript we write from left to right, but if you do the fraction order, actually we do it from right to left. Okay, just like this. So let's look at some example. For example, the first one, if you want to find the second partial derivatives of this function, so it means that you need to find all four of them, which is f sub xx, f sub yy, f sub xy, and f sub yx. Okay, you may have a question in your mind whether these two will be the same or not, because this one, the first one, you do the x first followed by the y, or you do the y first followed by the x, whether they are going to be equal or not. I mean, about 90% of the function that you are going to learn, the f sub xy and the f sub yx usually will be equal. Only some of them that is not, and actually there'll be a theorem, okay, to make sure that the f sub xy and the f sub yx will be equal. Okay, this theorem saying that if your f is defined on the domain which is called a disk D, and if your f contain the point AB under consideration that you want to find a derivative, and the function f of xy and f sub yx are both continuous on that domain D, then if you find f sub xy at the point AB and f sub yx at the point AB, they'll be the same value. Okay, so the most important condition is that your function f has to be continuous. Okay, it's to be continuous, and most of the time, I mean, the function that you consider in this course, usually it is a continuous, so that's why the f sub xy and f sub yx, they're the same. However, if you ask to find the second partial derivative, you still need to find all four of them as well. Okay, so let us first look at the f sub xx. Okay, to find f sub xx, you need to find f sub x first. Okay, so your f sub x, it is a derivative with respect to x, right? So the first one, you got a 2x, and the second one, your y is a constant, so your y, just pull it out, and the derivative go directly to the x alone, so a derivative, it is 1. And how about the last term, a derivative of y cubed, because right now your y is a constant, so a derivative just go to 0. So your f sub x is simply 2x minus y. Okay. Next, if you want to find f sub xx, so you further find a derivative with respect to x of this function. Are we good? You just put this function here. So the first term, you have a derivative of 2x, which is 2, because your x now is a variable, but your y is a constant, so you got a 0. So your derivative with respect to x twice, or your f sub xx, now it is 2. So look at the second one. If you want to find, let's say, f sub yy, okay, so of course first you need to find f sub y first. F sub y, look at the first term, it is x squared, but now the variable is the y alone, so that x squared is just simply a constant, minus this one, your y is a variable, your x is a constant, so you pull out the x, and the derivative of y with respect to y is simply 1. And the last one, a derivative of y cubed, you got 3y squared. Okay, 3y squared. So this one, you got 3y squared minus x. Okay, this is your f sub y. So to find a further derivative with respect to y, you just have this function here, 3y squared minus x. Okay, just plug in here and finding a derivative one more time with respect to y. The first term, you got 6y. Okay, very easy because your y now is a variable, but your x is a constant, so you got a 0. So at the end, finally, you got 6y as your f sub yy. Next, if you want to find f sub xy, so what does this mean? You need to find f sub x first, and then further derivative with respect to y. So it is a derivative with respect to y of f sub x. Here is your f sub x, right? So you just plug in 2x minus y. But now the first one, because right now your y is a variable, the first one is a constant because it contains only x, so you have 0. And a derivative go directly to your y, so you have minus 1. So you right now we got f sub xy becomes -1 at the end. How about f sub yx? F sub yx, actually f sub y first, and then further derivative with respect to x. Okay, so where is your f sub y? Right here, right? So you just plug in your f sub y into this one, and then you find a derivative with respect to x. The first term, you got a y, which is a constant in this context, so you have 0. The second term, you have a derivative of x with respect to x, so you got -1. So what happened? Now your derivative with respect to xy and a derivative with respect to y followed by x, they are the same. Okay, they are the same because this function, I mean, if you really take a look, it's just simply a polynomial in terms of x and y, and a polynomial usually it is continuous. So of course, as you can expect, that your f sub xy and f sub yx will be the same. Okay. However, I mean the order of derivative are not the same, right? So the order of calculation is pretty much different. Okay, as you can see. All right. So let's look at the next example. This one, what does this mean? You are going to start from the one inside. Okay, so the left to the right. Okay, so the first term that you are going to find derivative is your f sub y. Okay, so the derivative with respect to y, I mean, you have to pass the cosine first. So it's a negative of sine of the one inside, and then a derivative of the angle with respect to y. So you have x minus y plus yz. Okay, so what is the derivative of this term? First, it is the x. In this context, your x is a constant, so you have this one. I copied first. So the first one you got 0, and then your y, because right now your y is a variable, so you have -1, and your z is again a constant, and the derivative go directly to the y itself, so you have 1 again. So this one, your f sub y become, let's put it this way, I'm sorry, because here's a negative, so you got 1 minus z, and then side of x minus y plus yz, just like this. So this is the first derivative that we find. Next, you are going to follow by a derivative with respect to x. So to do the y, and let me just write down this way first. So we first do the derivative with respect to y and follow by the x. So it means that you're going to find a derivative with respect to x of this function. Okay, you just copy this one down, side of x minus y plus yz. Okay. So what happened? Because here in this context, a variable is the x alone. So this one is not a variable at all. So you can just pull it out, and then a derivative go directly to the one with a variable x. So a derivative of sine, you got a cosine of the one inside, and then using the chain rule, you pass your derivative to the inside function. Okay, so sorry, this one is the y multiply z. Okay, so you have 3 terms as the inside function. So the first one is the x. Let me just copy it down first. Okay, the first one is the derivative of x with respect to x, so you got 1. But the second one is simply simply a constant because it is a y. And the third one also is a y and z, so it's simply a constant, so you got 0 derivative. So it means that your f sub yx is simply 1 minus z and cosine of this angle, because this one is just a 1. Okay, so what's next? The third order that we need to find is the one with respect to z. So you have your f y x z. It is a derivative with respect to z of 1 minus z cosine of x minus y plus yz. So this one is a bit difficult because you see that you got 2 functions multiply each other. Both of them contain a variable z. Okay, so what you have to use is a product rule. So it is the first derivative of the second, which is negative sine, okay, the cosine derivative negative sine x minus y plus yz, and then a derivative of the one inside with respect to z, just like this. So this is the first derivative of the second plus the second cosine, just copy it down, derivative of the first. Okay, so you just try to finish it up. So this was a negative psi x minus y plus yz. So this derivative with respect to z of the x, it has become a 0 for the first one. It has become another 0 for the second one. And this one, the derivative go directly to your z, and your y is a constant, so you can pull it out. And derivative of z with respect to z, you got 1. And the second term, this one you just copy it down. And the derivative of a constant 1, it is 0, of course. A derivative of z with respect to z, you got a 1. Okay. So finally, if you simplify it a bit, the y derivative of f with respect to y, x, and then z becomes a what? Y. Okay, so I just put this y up front, and then this one become a z minus 1 side of x minus y plus yz. Okay, and then this one I just put it up front, minus cosine of x minus y plus yz. Okay, so this is your third order derivative, partial derivative that you find. Okay, but we still need to do the last fourth order here further with respect to x. So now you have f sub y x z already, so you do further one with respect to x. So it is a derivative with respect to x of this whole function. You just copy down first, x minus y yz minus cosine of x minus y and yz. Okay, so here there are no x in this function, right? So you can just pull it out, okay, from the derivative. So you got y z minus 1, and then the derivative go directly to the side, which you have cosine of x minus y plus yz, and the derivative of the angle inside. Okay, and the second term, a derivative of cosine, it is a negative sign, so with the negative here, so you have a positive x minus y and yz, and then a derivative of your angle inside as well, okay, with respect to x. So just be patient and try to finish it up. This one is cosine x minus y yz. So the derivative of this one with respect to x, the first one is 1, the rest are 0. Okay, and here also the side of x y yz, and then what's the derivative of this one is 1, and the rest will be 0. Okay, so I just write this one here, 1 minus 0 plus 0. Okay, so this means that at the end what you need is a derivative of f with respect to y x z. X is going to be y z minus 1 cosine and sine. Okay, so hopefully you can follow step by step to find each of the derivative, okay, in either the first order, second order, third order, or the fourth order, okay, of this function. Okay, just be careful which one is a constant, which one is a variable. That's the most important, so that you can decide whether you are going to need the product rule or the quotient rule or any kind of derivative rule that you need to apply. All right. The next problem, for somebody, they may say that, hey, it is a little bit difficult because this one is the one that you are going to go back to a definition. So don't forget that your d1f, or it is the same as your f of x, or it is the same as your d by dx of a function f. It is a limit as your h goes to 0 of your f of x plus h, and then y minus f sub xy over h. Okay, and in a different token, if you want to find a derivative with respect to y, definition saying that you just fix your x and then let your y change, okay, over a small change of y. That will be a derivative with respect to y. Okay, so now let us go ahead and calculate the derivative with respect to x of this function at this particular point. Okay, of course, I mean this one we let your y is not 0 first. This one we let your x is not 0 first. Okay, so let's look at your first one. Let me add one more page here. So your d1, I mean we let your y is not 0 first, and then let's look at the first problem, the d1 of f at 0y. So it is the one that your x change, right? So you are going to find the limit as h goes to 0. Your x at the beginning, it is 0. You see, it is already need to find a derivative at this point. So it is a 0 plus h. You see, just using this formula, but the x right now is the one that you need to find the derivative at this point, 0. And then your y arbitrary minus f at 0y over h. Okay, now because your h just go close to 0, so of course it is not 0, and your y is already let to be something that is not 0. So this means that this function, it is go into this category, right, that your x and y is not both 0. So we are going to have the, I mean, use this formula for the function to find the limit. So this one, you got your x to be h, your y just a y, and h square minus y square over h square plus y square. We get the first component is the h, right? How about this one? This one, your first component is a 0. So again, it is falling into this category because your y is not a 0, right? So you plug in your x as 0. So it is a 0 over something that is not 0. So it's just simply a 0 anyway, right? And then don't forget that you are going to divide the whole thing by h. So it means that you can just cancel the h, okay? And then you are going to let your h goes to 0. So this one is gone, this one's gone. So what you end up with, it is negative y cube. You see y cube here, and then over y square. And because your y is not 0, so you got negative y. Okay, so this one is your d1 at d1f at the point 0y, where your y is not 0. So let's look at the second problem. The second problem, you want to find d2f at x0, where your x is not a point 0. So you start by letting your x is not 0, then you are finding the limit h goes to 0 of f. Right now it is d2, so the only thing that's changed, it is your y. So it is the x that's fixed, okay, but your y If you look at the definition, okay, if you look at the definition, a derivative with respect to y, it is x, y plus h. But right now, your y, the point under consideration, it is 0. So you have a 0 plus h. And this one is 0. See? This is the difference in y over h. Now, which formula of a function that you are going to use? Okay, again, this one, because you end up with x and h, and your x is not 0 at the beginning. Your h, you're finding the limit as your h goes to 0, so this one is not 0 as well. So we are going to use this formula of the f again. Okay, so it is the arbitrary x, but your y right now, it is the h. You see, your second component is this h, and then x and h square over x square h square. Okay, just replace your y by h square minus f at x 0. So your x is an arbitrary x that is not 0, and your y fixed to be 0 already. So as you fix your y to be 0, you got a 0 over x square, which is 0 again, over h. Okay, don't forget this one. So as you continue, you can see that this h cancel, and then as your h goes to 0, this one goes away, this one goes away, but this one still has the x cube. So you got x cube over x square, and your x is not 0, so you got x at the end. So this was your d2f at the point x0, where your x is not 0. So you got what they want to show, right? That d2f at x0 is x whenever your x is not 0. However, what are we going to do next is to find d12 and d21 at the point 0, 0, and then see whether they are equal or not. Actually, they just let you guys know that, hey, these two quantities are not actually equal. So this will be the example of the function, I mean a rare case, as I told you. Okay, this is a rare case that your f sub xy and f sub yx are not the same at some particular point. Okay, now let us show how to verify this one. Okay, start from the left hand side and then follow by the right hand side and make sure that they are not equal. But before we do that, let us make sure first that you know how to find also d1 of f at 0, 0 and d2 of f at 0, 0. So we first begin with to verify or to find what is the d1 of f at 0, 0. So this one is actually the limit as h goes to 0 of f. This one is the change in x, so it's 0 plus h, and then 0 minus f at 0, 0 over h. Okay, so this one is actually f at h0, and your h is not 0 at this context, right? So we are going to use the one up here, okay, as a formula. But now your second component is 0, so everything is gone. So we have a limit, a limit as your h goes to 0 of 0 minus, how about f at 0, 0 is already given to be 0, so it's here over h. So it means that this fraction equals to 0 before taking the limit. So the limit of a constant, it just goes to 0, right? On the same token, if you want to find d2f at 0 0. This is pretty easy because it is h, the limit of h goes to 0. Now the change it in the y component. Okay, however, even though you look at the y component, this one is still f at 0h and your h is not 0 again. So we are using this upper formula, but right now your x is 0, so everything is gone again. So what you end up with is a limit as your h goes to 0 of 0 minus 0 over h again. So it is a fraction, that is equals to 0 at the beginning before taking the limit. So a limit of a constant is just simply 0. Okay, so after you have these two quantity, we are ready to find d1 f at 0 0 as we promised. So this one is actually the first derivative with respect to x, and then the second derivative with respect to y. So now here's the d by dy, okay, the one outside, and then d1 f at 0 0. So you are going to regard this d1 f as a function, let's say g. Okay, so this one you are going to find the derivative with respect to y of a g at 0 0. Then what happened? It is a limit as h goes to 0 of g, right, g, and then the change is in y, so it is 0 and 0 plus h, let me just make it clear, and then minus g at this point 0 0 over the change h. Okay, and if you look at this one carefully, this is d1f 0h, right? And then here your h is not 0 again in this context because you are taking the limit as your h go close to 0, right? Do we have this one before, d1f at 0 and some point that is not 0? We did it right here, you see, d1f 0y, when your y is not 0, you got negative y. All right, you got negative y here, but in this context you just have d1f of 0h. So what you are going to have is going to be the negative h instead, minus d1f at 0 0 is already here, right, 0 over h. So the h and the h cancelled, so you end up with a limit of negative 1, which is negative 1. So this one is your d12 f at 0 0. How about d21 f at 0 0? You do the same thing. You are going to find a derivative with respect to x, you see, further with respect to x, and then d2 f at 0 0. Okay, because here's the first one. And then now you regard your d2 as a h, as a capital G. You can look at it as a function capital G, and you need to find a derivative of this capital G with respect to x at this particular point. So it is again the limit, okay, as your h goes to 0 of g, your x change, your y is fixed, minus g of this point over h. Okay, but again this one, it is d2f at h 0, and your h is not 0. We already found it right here, d2f at x0, where your x is not 0, you got simply an x. But in this context you have d2f of h instead. So what you end up with is a limit as h goes to 0 of h minus d2f at 0 0. We have it here, which is 0 over h. So the h and the h cancel, so you have a limit of 1, which is 1. So it means that now your d12 is negative 1, but your d21 is 1. so they are not equal. Okay, but as I told you, this is the some of the rare case. Okay, usually the D21 and D12, they are usually equal. I mean 90%. This is only the rare case. Okay, however, you may need to go ahead and try to um, review yourself again on what we did here about the higher derivative, how to find a further derivative from the first one. Okay, and to continue with further derivative higher and higher. Okay, so we are going to stop the video clip of this one right here. Okay, and we'll see you next time on functions of several variables in other sections. We'll see you.